Hello and welcome back to the YOLO Family series. And in this video, we're going to talk about YOLO version 3. And the topics that are going to be covered in this video include an introduction to the YOLO version 3. And in the second section, we're going to look at the architecture of YOLOv3 in detail. And finally, we're going to talk about the output predictions and the predictions at different scales implemented in YOLO version 3. So YOLO version 3 is a popular convolutional neural network for real-time object detection, published in 2018 by Joseph Redman. And during its release time, it represented the state-of-the-art for this task, ensuring accurate and fast performance like never before. And even today, it is still a more than valued tool. And when they trained the YOLOv3 model using the Titan X GPU, it can greatly process images of resolution 320 by 320 at 45 frames per second, and that's a very good inference speed. Unfortunately, YOLOv3 was the last work that was handled by Joseph Redman, who can be considered as the father of the YOLO family. And he said to have left the research in this field after YOLOv3 was used for military purposes, which was unwelcome to the author of the original YOLO. And even though there were a lot of versions which were released by different people after he stopped working on YOLO, he only recognized YOLOv4 as a true worthy successor of YOLOv3. Now that we have seen the introduction to the YOLO version 3 paper, let's consider the inputs to the YOLO model. So YOLOv3 takes input images of size 416, 608, 832, and 1024, and multiplied by the number of channels. And we're going to use 3 if it is an RGB image, and we're going to use 1 if it is a grayscale image. And we can use an input dimension of n by 416 by 416 by 3. If we have n to represent the batch size and 3 to represent the number of channels for the image. And these dimensions are not casually selected. They must be divisible by 32. So we're not just selecting these numbers randomly. We're handpicking these numbers because we want to detect objects at different scales in the YOLO architecture. So these numbers must be divisible by 32. And if they're divisible by 32, that means they're divisible by every number that is a factor of 32. So they will be divisible by 2, 4, 8, 16, and so on. Of course, the network is able to process images of any size as long as they are resized to the aforementioned dimensions. So even if you have an image of a different input size, you have to resize that image so that it can be it can fall between the range of these values. And whenever you resize the image, you can just resize or crop the image, or if, maybe you can maintain the aspect ratio of the image so that it doesn't become distorted when you input the image into the model. In the second section of this video, we're going to talk about the architecture of YOLO version 3. Last time when we talked about YOLO version 2, we used a Darknet 19 classification network as the backbone or the feature extractor for YOLOv2 model. Now in YOLOv3, we're going to use a much deeper network known as Darknet 53. And as you can see from the name, the 53 just represents the 53 convolutional layers used in YOLOv3. And detection is going to be performed at 3 different scales. And these are shown in the image. So the backbone is just a classifier network, and it will be trained first. So the new network is a hybrid approach between the network used in YOLOv3 and a residual network such as ResNet, so that it has some shortcut connections. As we can see in the image, when we see the residual blocks, they're implemented within those blocks that are being repeated many times. And skip connections are another key concept of YOLO version 3. And it is empirically known that deeper networks struggle with learning simple functions such as the identity function. So these functions are well estimated in the very first layers, but their quality degrades as the network gets deeper and deeper. Skip connections solve this problem. Usually in a neural network, the output layer constitutes the input of the next one. So the reason that they use residual networks or skip connections is because deeper network, such as residual networks, they struggle with learning simple functions such as identity function. And these skip connections helped to preserve some of the information from the shallow part of the network. And the quality degrades when the network gets much deeper. And skip connections offer a solution for this problem. After training on classification, the fully connected layer of the Darknet 53 backbone will be removed because we want our model for detection. So the first task will be, just like we did on YOLOv3, we're going to train the backbone for classification first using a classification dataset such as ImageNet. And the last layer is a fully connected layer for the classification task. So whenever we want to implement the detection first, we have to remove the fully connected layer of the backbone. So skip connections allow one layer output to bypass the immediately following layers in order to be considered again later. So as we can see from the image, if we have an input of X, we can just directly pass that input information. And on the second partition, we're going to pass it through multiple convolutions. So with this approach, the simpler information, referred to as the residual block, the one that we did not perform any kind of convolutions, is stored and preserved. And on the other hand, the more complex information, which is extracted by passing through multiple layers as usual. So subsequently, the simple, which is the residual block, and the complex information are going to be combined with a sum operation. And going back to YOLOv3, it is made up of the Darknet 53 backbone. So the Darknet 53 has 53 convolutional layers, and we're going to add 53 additional layers, which are going to be used for the detection task. So the entire architecture of YOLO version 3 is going to have 106 layers. YOLOv3 struggles with detecting small objects. However, with YOLOv3, we can see we can get a better performance for small objects. And that is because of using these shortcut connections that we introduce. Using these connections method allows us to get a more finer grained information from the earlier feature map. As we have seen previously in the YOLOv3 video, we have also introduced a method known as fine-grained information, in which we pass some of the information from a previous layer and concatenate or merge with the layer that's 13 by 13. So this helps to enhance learning for detecting smaller objects because smaller objects are detected earlier in the network. And if they're not propagated as we go deeper inside the network, their performance is going to degrade. However, comparing to the previous version, YOLOv3 has worse performance on medium and larger size objects. Now that we have covered the backbone section of the YOLOv3 architecture, unlike YOLOv1 and YOLOv2, which predict the output at the last layer, YOLOv3 predicts boxes at 3 different scales, as illustrated in the below image. So in YOLOv2, we performed detections, or the prediction boxes were being predicted on the last layer, which has a 13 by 13 dimension. And in YOLOv1, we used a 7 by 7 output. And there is only one scale, so we can only perform detection within that scale. But in YOLOv3, the detection was performed on 3 different scales. So at each scale, YOLOv3 uses 3 anchor boxes and predicts 3 bounding boxes from the anchor boxes for any specific cell. And each object is only assigned to one grid cell in one object, in one detector tensor. So once we have the feature map from the 19 by 19 output from the Darknet 53 backbone, we're going to add more layers, and these are called the detection blocks, which are shown in the boxes that are colored pink. And we're going to perform the first detection. And second, we're going to do the same. And we're going to pass some of the information from the previous layers. And we're going to concatenate, and then we perform the second detection. And then we do the same for the third detection. So features are extracted from these scales, like the feature pyramid network that we have seen in a previous video. Several convolutional layers are added to the base feature extractor of the Darknet 53. Next, the feature map is taken from the previous 2 layers and is upsampled by 2 times. So from the shallow part of the network from Darknet 53, for example, from the part where the spatial dimension of the feature map was 76 by 76, we're going to take that information and we're going to concatenate with the one that's coming from the second detection. And the second detection is going to be upsampled by 2 times. So we're going to increase the spatial dimension by 2 times. So when we upsample, its spatial dimension is going to be the same as 76 by 76. Because when we perform concatenation, they must be of the same spatial dimension. That means the width and the height of the image or the feature map must be the same. So a feature map which is taken from earlier in the network will be merged with the upsampled feature using concatenation, and the last of these layers will predict the bounding box, the objectness score, and the class predictions. Passing through the Darknet 53 backbone, the extracted feature maps are scaled to the sizes 76 by 76, 38 by 38, and 19 by 19 by using strides with values of 8, 16, and 32 respectively for an input size of 608. So if you consider an input size of 608, which is perfectly divisible by 32, and you perform a convolution by using stride of 8, 16, and 32 respectively. When you reach the layers 82, 94, and 106, you'll have the spatial dimensions of 76, 30, 38, and 19 at the 3 different scales. And if we use an input image of 416 instead of 608, so the spatial dimension of these output feature maps at layers 82, 94, and 106 will be 13, 26, and 52 respectively, as we can see from the image on the left side. And notice that we can detect objects of different sizes at different scales. That means large objects are detected using the smallest scale of 13 by 13, and small objects are detected using the scale of 52 by 52. So, as I mentioned previously, if you want to detect small objects, you have to use a smaller spatial resolution. And if you want to detect large objects are detected using a small spatial dimension, and small objects are detected using the 52 by 52. So as you can see on the image, large, medium, and small are divided according to the different scales where we are performing the detections. So 13 by 13 is responsible for predicting large objects. 26 by 26 is responsible for predicting medium objects. And 52 by 52 is responsible for predicting small objects. Next, before we see the prediction bounding boxes, we're going to look at the anchor boxes. When we talked about YOLOv3, anchor boxes were introduced for the first time, and they describe the most recurring width and height ratios in the ground truth. And for each scaling step where we're performing the detections at 76, 38, and 19, 3 anchor boxes will be extracted for an overall of 9 boxes. So at the 3 different stages, we're going to have 3 anchor boxes, and in total, we're going to have 9 anchor boxes. Anchor boxes are used at inference time to guide the definition of the candidate's bounding box size. So we're going to use these 9 anchor boxes in order to find the right dimensions for the bounding boxes. And these are expressed in terms of the width and the height ratio of the most suitable anchor box. As we have seen in the YOLOv3 video, we used a k-means clustering to find the initial anchor boxes. So these 9 anchor boxes are selected by using k-means clustering on the COCO dataset. And you can watch that video in order to understand how these anchor boxes are going to be selected. Next, once we have defined the anchor boxes, we're going to describe the bounding box predictions. On the COCO dataset, 3 boxes are used at each scales. So we have defined 3 anchor boxes at 3 stages. So we're also going to have 3 boxes in each scale. Therefore, the output tensor is going to be the dimension of the image, n by n, then b multiplied by 4 plus p note plus c. 4 represents the bounding box offsets, 1 represents the objectness prediction, and 80 represents the class predictions. B stands for the number of bounding boxes identifiable for each image cell. In other terms, for each cell of the image, YOLOv3 tries to predict B possible bounding boxes of belonging. In YOLOv3, B is equal to 3. So each grid cell for the output image is going to predict 3 bounding boxes, and B represents that number. P note is the objectness score. It describes the probability that the cell of interest is the center of the bounding box and is consequently more significant. So P note is just the same as the one that we have seen in a previous video, but we used a different notation of PC. It's going to describe whether there is going to be an object inside the bounding box, and if there is an object, that value is going to be 1. Next, we're going to have 4 box predictions, which represents the number of attributes describing each candidate's bounding box. So the coordinates for the center of the objects are going to be described by using Tx and Ty, which are going to be the offset of the center of the bounding box with respect to the cell of interest. And Tw and Th are going to be the size of the bounding box expressed as the scale of the most suitable anchor box. And we have seen these offset values from a previous video. For instance, if the anchor box has a size of 100 by 100 and the bounding box has a size of 90 by 80, then Tw and Th are going to be represented as 0.9 and 0.8 because we're going to divide these values by the width and the height of the image. And these coordinate box predictions, which are 4 of them, are going to be values which are going to be outputted by our model during the training procedure. And they're going to be optimized in order to transform the anchor box to the predicted bounding box. So Tx, Ty, Tw, and Th are predicted as offsets to the anchor box. They are output after training the neural network, as I have mentioned previously, and all values must be normalized in order to avoid unstable gradients. So Cx, Cy, Pw, and Ph, where Cx and Cy are the offsets directly from the top left corner of the image, and Pw and Ph, which represent the width and the height of the anchor box. All of these values must be divided by the width and the height of the image, respectively, as we can see on the image on the top left corner. And the reason we're doing this is because we don't want the values to be outside of 0 and 1, to be outside of the range in 0 and 1. And we're going to do the same for the Tx and Ty coordinates, which are going to be passed through the sigmoid activation function, which is represented on the image on top. When we compute Bx and Py, Bx and By, we're going to pass the Tx and Ty inside a sigmoid activation function, and we're going to add the offset from the top left corner of the image because the grid cell is in a different position from the top left corner of the image, so we have to add the offsets. And these Cx and Cy values are already normalized, so we need to normalize the Tx and Ty values as well before we add them together in order to find the coordinates for the bounding box. Finally, we need to multiply the bounding box predictions Bx, By, Bh, and Bw to get uppercase Bbx, Bby, Bbw, and Bbh, which gives us the absolute values. So once we find the coordinates for the predicted bounding box, we need to multiply them again with the width and the height of the image. which is going to be which is demonstrated on the image on the right side. And transforming the anchor box to the predicted bounding box is called the log space transform. So we have already seen how to compute these values in detail in the video about YOLOv3. So you can take a look at that video in order to understand the concept of how to compute the bounding box coordinates from that video. So the remaining part will be the class predictions. So C stands for the number of recognizable classes. Therefore, C values from P1 up to PC describes the probability that the bounding box belongs to each of the known classes. And since most of the YOLOv3 distributions are pre-trained on the COCO dataset, which describes 80 different classes, in our case, we will say that C is equal to 80. And by using the equation B multiplied by 5 plus C, we can calculate the predictions for each grid cell. So each grid cell is going to contain 3 bounding boxes. So B will be equal to 3. And we have 4 box coordinates, which are going to be parameters that are computed from our training procedure, which are tx, ty, tw, th, which describes the offset from the anchor box. And when we pass these values in the equation we have seen on the previous slide, we can compute bx, by, bw, and bh. And we have one objectness score, which is going to describe whether there is an object within the bounding box. And we have 80 different classes. So in total, we multiply 3 by the summation of 4 coordinates, 1 objectness score, and 80 different classes. And in total, we're going to have 255 predictions for each cell in the output. So let's take a look at the outputs from the different scales. So detections are made at layer 82, 94, and 106. So for an input size of 416 by 416 by 3, we can have an output of 13 by 13 by 255, which is going to be the output on layer 82. Then we have 26 by 26 by 255, and which is going to be the prediction from the second layer, and 52 by 52 by 255, which is going to be the prediction for the final output. And the 255 is the one that we have seen from the previous slide, the values that we computed, which is going to get the predictions for the 3 bounding boxes. For an input size of 608, we can have an output of 19, 38, and 76. Now, we have mentioned that we can get predictions at different scales. So let's take a peek at the detection that is being performed on these different scales. So on the first prediction, let's assume the input is 608. The first detection occurs at the 82nd layer, and it is responsible for recognizing the largest subjects within the image. So it's going to detect the large objects. Here, after passing through the Darknet 53, the feature map has a size of 19 by 19. So right after we finish the convolution operations from the Darknet 53 backbone, the output dimension will be 19 by 19. So for the sake of simplicity, we will now refer to the feature map as just an image size of 19 and 19, and we do not involve the depth. So therefore, the image is subject to a convolution operation again, with a kernel size of 1 by 1. And the output of this convolution will have the dimensions 19 by 19. Then we have the 255 values, which are going to be outputted by each grid cell. So that's going to be the dimension in order to detect the first object. To recap, 3 bounding boxes are identified for each image cell. For an overall of 19 by 19 by 3, we're going to have a 1083 bounding boxes at the first detection stage. So on the first stage, we're going to have a spatial dimension of 19 by 19, and the depth will be 255. And since we have 19 by 19 grid cells, we're going to multiply the two numbers. Then we're going to multiply 3, which represents the number of bounding boxes that we're going to predict for each cell. So in total, we're going to have 1083 bounding boxes. Each bounding box is described by the following values. So the 3 bounding boxes that we're going to predict has the coordinate values tx, ty, tw, and th, and p naught will be the objectness score, and p1, p2 up to pc are going to be the class scores. The class score for each bounding box is given by multiplying the objectness score by the highest probability of belonging to a class. So we're going to multiply the objectness score p naught, and we're going to take the values outputted for each class, and we're going to put them inside a vector. And after we multiply these two matrices, it's going to be an element-wise operation. So since p naught is going to be a constant, we're just going to multiply p naught by every single value inside the vector for each class. Then we're going to take the maximum value from the output, and that's going to be the class score for that bounding box. So on the image, we can see that we have 3 bounding boxes, and we have 3 bounding box class scores, and each of them are computed by using the method that I just explained right now. Now, let's talk about the second object detection. Once we have finished the first, once we have detected the first object, the next step will be to compute the predictions for the second object. The image of size 19 by 19, the ones that we have computed from the first detection, is going to be upsampled, and its spatial dimension now is going to be 38 by 38, and passes through several convolutional layers and skip connections. So we're going to pass the output from the spatial dimension of the feature map from the Darknet backbone is going to be 38 by 38. So we're going to pass that value directly from the Darknet backbone, and we're going to concatenate with the output from the first detection after being upsampled. So before the second detection, the image is concatenated to the one coming from the 61st layer, having the same size of 38 by 38. This is because the current image can be thought of as a low resolution image. whose features have been widely processed. Vice versa, the output of the 61st layer is an image with a higher resolution, whose features have not yet been sufficiently processed. So since the one that's coming from the first detection has been processed multiple times, the one that's coming from the 61st layer of the Darknet backbone is not processed by different convolutions. It's going to preserve some of the information coming from that layer. And when we concatenate them together, it's going to enhance and improve the detection results. So the second object detection occurs at the 94th layer, and it is responsible for recognizing the medium-sized subjects within the image. So this second detection that we're performing is going to detect the medium-sized objects. And it works exactly like the first detection. And this time, we're going to have a spatial dimension of 38 by 38. And each of those grid cells are going to predict 3 bounding boxes. So in total, we're going to have 4,332 candidate bounding boxes that are going to be extracted from the second detection. Once we have finished the second detection, in the same way before the third detection, the image of size 38 by 38 is going to be upsampled to 76 by 76. So the one that we got from the previous detection is going to be upsampled again, and it's going to be changed to 76. And this is because we're going to go further back in the Darknet 53 backbone, and we're going to bring back that 76 by 76 feature map, and we're going to pass it directly and concatenate the feature map with the one that's just computed now. And it passes through further convolutional layers, which are shown by the box that is shown in pink color. And it is concatenated with the 36th layer, having the same spatial dimension. So the reason that we are performing the upsampling is because we want the spatial dimension to be the same so that we can concatenate them together. And the reason that we're performing a bunch of convolutions is to enhance and reduce some of the feature maps. Finally, the third and last object detection occurs at the 106th layer, and it is responsible for recognizing the smaller subjects within the image. So this particular stage is going to detect large objects. And now, since we have a spatial dimension of 76 by 76, and we have 3 bounding boxes, in total, we're going to predict 17,328 bounding boxes that are going to be extracted at this stage. Finally, after we have detected and predicted all of the bounding boxes from the 3 different stages, there is only one step left. After the 3 stages of object detection are completed, we have an overall of 1,083 plus 4,332 plus 17,328 bounding box predictions. So in the entire YOLOv3 network, we're going to predict 22,743 candidate bounding boxes, each with their own class score. And we have seen how to compute the class score in a previous slide. Of course, not all of them represent a good result, so we need to filter them using the non-maximum suppression algorithm. This can be done by using the algorithm we implemented in the previous section when we discussed about nanomaximum suppression. Finally, let's talk about the class predictions in detail, because the class predictions used in YOLOv3 are not the same as the ones that are used in YOLOv2. In YOLOv2, when we performed the class predictions, and specifically when we talked about YOLO 9000, we used a softmax layer in order to predict the classes. But in YOLOv3, we're going to use independent logistic classifiers, and binary cross-entropy laws are going to be used because there may be overlapping labels for multi-label classification, such as if the YOLOv3 is moved to other more complex domains, such as open image dataset. So what is this multi-labels predictions, and what makes it different from the predictions we have seen in YOLOv2? In some datasets, like the open image dataset, an object may have multi-labels. For example, an object can be labeled as a woman and as a person at the same time. In this dataset, there are many overlapping labels, and when we use softmax for the class prediction, it imposes the assumption that each box has exactly one class. Softmax only assumes that you have one class for each box, for each bounding box, which is often not the case as in the open image dataset. For this reason, YOLOv3 does not use a softmax layer. Instead, it simply uses an independent logistic classifier for any class. And when you use a logistic classifier, they calculated the loss by using binary cross-entropy loss for the class predictions. And binary cross-entropy loss is just finding the difference between the true label and the prediction from our model, subtracting them, and then squaring that result. Then we sum them together and we divide by the total number of images in our training dataset. So using an independent logistic classifier, an object can be detected as a woman and as a person at the same time. So when we replace the softmax layer that we have used in YOLOv2 and change it by the logistic classifier, now our bounding box can predict a woman or a person at the same time. So it might have different labels, but each class prediction is going to be outputted using a different classifier. So here are some notes that I might have mentioned them when I discussed about YOLOv3, but they're very important. So I need to emphasize them using this slide. So both YOLOv2 and YOLOv3 also use batch normalization. We have mentioned previously in the video about YOLOv2 that batch normalization was introduced. And we're going to use batch normalization also in YOLOv3. The leaky ReLU activation function was also used in YOLOv3. The leaky ReLU activation function has been used starting from YOLOv1 up to YOLOv3, and it's going to be replaced when we talk about YOLOv4. When we perform the convolutions in YOLOv3, remember that there are no max pooling layers. And max pooling is different from convolution because if you have, when you want to convolve an input image, or let's say a feature map, and you have a filter which is 2 by 2, And when you perform max pooling, you're selecting the maximum number and you're moving the filter from the top left corner of the image and up to the bottom right corner of the image. And when you just select the maximum values, you're ignoring the rest of the values. So they have no contribution at all to the output. So let's say for this example, as we can see on the image, when we just select the maximum of the 2x2 area, and we have a stride of 2, which means we move the sliding window by 2 pixels at a time to the right. Then we select the maximum values 10, 23, 11, and 25. And in this case, we do not consider the rest of the values. But in the case of YOLOv3, all of the layers are convolutions. And when you use convolutions, you're taking into account all of the numbers and all of the pixel intensities within your image. So if you want to reduce the spatial dimension of the input image, you can just use a stride of 2, because max pooling is mostly used with a stride of 2 in order to reduce the spatial dimension. So you can do the same by using a convolution, a normal convolution with a stride of 2, if you just want to reduce the spatial dimension. Because as we go deeper inside the network, we want the spatial dimension, or the width and the height of the feature map, to get smaller and smaller. So this will prevent loss of low-level features, since max pooling only selects the maximum number and ignore the rest within the sliding window. Finally, let's take a look at the performance of the YOLOv3 model. For overall, the mean average precision, YOLOv3 performance has dropped significantly. As we can see on the graph, when we compare the performance of YOLOv3 with other architectures that were released at the same time, we have RetinaNet and we have SSD. And when we compare the result from the YOLOv3 608, when we use an input image of size 608, we got a mean average precision of 33% in 51 milliseconds inference time, while a similar model, the RetinaNet 101-50-500, only got 32.5 mean average precision in 73 millisecond inference time. So RetinaNet was the state-of-the-art model during that time. So YOLOv3, although the mean average precision is catching up with the RetinaNet, the inference speed is the one that we need to emphasize, because the reason that we are implementing YOLO is because it enhances the performance, and it also reduces the inference time in order to give the predictions. And YOLOv3 is also on par with SSD variants and with 3 times faster, and it's also 3 times faster. So as we can see on the graph, the YOLO models are represented by using the star, and other models are represented by using either the letters and in case of the RetinaNet, it is represented by using the purple color and the orange color. So on the y-axis, we have the average precision, and on the x-axis, we have the inference time. So if you want a state-of-the-art model, that model needs to have a smaller inference time, so it has to be on the left side, further to the left, and it needs to have a very high mean average precision. So in this case, you need a model that's going to be on the top left corner of the graph. So as you can see, the YOLO model, although it is not performance-wise or in terms of average precision, it's not as high as RetinaNet, but in terms of inference time, it is the furthest to the left when compared to the rest of the models. So it's very, very fast. But when you compromise for the performance, then you will get a higher speed. So that's what we're seeing or taking into consideration when we're implementing this kind of model. So this is all about YOLOv3, and in the next video we will take a look at YOLOv4.